Okay, hi everyone. We're talking about chapter 3. And here's my 1-minute summary. We started talking about the Carnot cycle. Carnot told us that it was impossible to devise an engine which had 100% efficiency. I always had to have some waste heat. We used the Carnot cycle in order to define entropy. Specifically, we have this formula, delta S is Q reversible divided by T. This reversible is incredibly important because it tells us that in order to calculate an entropy change, you have to utilize the heat that would be transferred along a reversible path, even if the actual path is not, in fact, reversible. We then derived all of these formulas to calculate changes in entropies for different types of processes, constant volume heating, isothermal expansions, et cetera, et cetera, et cetera. But you may be scratching your head and thinking that there's this really big question which he hasn't answered, which is, what is the second law of thermodynamics? Wait no more, I'm about to tell you today. Here it is, it's actually discussed in Atkins 3a, but what the second law of thermodynamics says is the following. The entropy of an isolated system cannot decrease when a spontaneous change occurs. In more everyday language, we say the entropy of the universe tends to a maximum. So the energy of the universe is constant, the entropy tends to a maximum. We'll flesh that out for you a bit today. And I want to do that by going back to these two examples that we started with in an earlier video. So imagine these two types of processes, the isothermal reversible expansion of an ideal gas and the isothermal free expansion of an ideal gas. Initial and final states are the exact same between these two. I'm imagining that it doubles in volume. And again, I'm trying to give you a physical picture as to what's going on. In the free expansion, you might imagine this two-bulb system. Half of it is vacuum. The other half is filled with gas. Once you pull the stopcock, it automatically expands. Whereas in the reversible process, you have to imagine heating it at some incredibly slow rate, an infinitely slow one, so that all of the heat is converted to work and it just slowly expands without increasing its temperature. Now the formula that we just talked about, Q reversible divided by T, tells us that the change in entropy for these systems, or for these two paths, is the same. Entropy is a state variable. So in both cases, delta S is NR natural log VF over VI. But in terms of what actually happens, then there's this giant difference between these two. If you stop and think about it, what you'll recognize is that this free expansion occurs automatically. Once you pop that stopcock, the gas spreads and there's nothing you can do to stop it. So the specific thermodynamic language that we use for this is to say that it's spontaneous, or it's irreversible. This contrasts with this example, the reversible, the infinitely slow process. This does not occur automatically. And instead we say that it's reversible. It's balanced, where the system and surroundings are always in equilibrium. And the last question to sort of ask yourself as you parse through this is, well, where is the difference between these two? If the change in entropy is the same, where's the difference? And the answer is, it's in the surroundings. So here's how you can think about this. Here's my surroundings. We usually think of them as a giant bath. Here's the system. The heat from one is related to the heat of the other. They are equal and opposite. So Q of the system is equal to negative Q of the surroundings. This is always true, right? It's a statement of the first law of thermodynamics. I can't create any energy. But it will turn out that Q reversible of the system is not equal to negative Q of the surroundings. Why? Why is that true? Well, simply, it's because not all paths are reversible. So the Q of the system is not the same as Q reversible unless it is in fact a reversible path. What this means, however, is that the reversible heat of the surroundings, Q reversible of the surroundings, is always negative Q of the system. Q reversible of the surroundings is always a state function. And you're probably scratching your head and going, why in the world is he telling me all of this? This is like circular arguments. A is equal to B, but not equal to C, blah, 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 blah. But it gets to be incredibly profound. Imagine I started dividing the universe up into the system and the surroundings. So delta S of the universe is delta S of the systems plus delta S of the surroundings. I now plug in my definitions. Delta S of the universe is Q reversible of the system divided by T plus Q reversible of the surroundings divided by T. I then take this last definition and plug that in for Q of the surroundings. So Q reversible of the surroundings is negative Q of the system. And you get this incredibly powerful statement. Let me show you why. Again, consider these two examples, the isothermal reversible expansion and the free expansion. The change in entropy of the system is the same in both cases. Initial and final states are the same, therefore delta S is the same. It's NR natural log 2. You go back and do your thermodynamic cycle analysis. Excuse me. Q of the system is nRT, natural log 2. If I look at delta S of the surroundings, I take negative Q of the system, divide it by T, and I get negative NR, natural log 2. When I add all of these up, delta S total, delta S of the system plus delta S of the surroundings, it equals 0. These are equal and opposite. However, in this case, the free expansion, Q is 0, work is 0, Q is 0. Therefore, delta S of the surroundings is 0, and you end up with this. Delta S top equals delta S of the system plus delta S of the surroundings equals not 0. This is incredibly important. What you can see in comparing these is that when a spontaneous change occurs, delta S total is greater than 0. Whereas when a system is at equilibrium, delta S total is equal to 0. So we often combine these into a simple statement of the second law of thermodynamics. Another way we can say the second law of thermodynamics is simply that delta S total is greater than or equal to 0. If the total change in entropy is greater than 0, a spontaneous change occurs. And you know lots of places where this happens. So imagine here's my system. It's some liquid water, and it's in a freezer at minus 10 degrees. This is the surroundings. What happens over time? Well, you're going to get ice. Right? The liquid will freeze. You'll get solid ice, and this will warm up a little bit. Another example. Imagine I have two copper blocks, one at 0 degrees, one at 100 degrees. They're in thermal contact. What happens over time? Right? Well, they're both going to end up at 50 degrees. In both of these examples, a spontaneous change occurred. Ice, or I should say liquid water, spontaneously formed solid water. In this case, heat spontaneously transferred from the warm object to the cold one. And whenever a spontaneous change occurs, we know delta S total is greater than or equal to 0. Where this will ultimately be used is in chemical reactions, which we don't know whether or not they will occur. If we can calculate this delta S total, we can figure out whether or not a chemical reaction will occur. And I just want to point out to you that this is really a powerful technique. So entropy is sometimes called the arrow of time because it is the increase in entropy of the universe, the second law of thermodynamics, which is causing this process to always go this way. Okay? There is nothing in the first law of thermodynamics which would prevent the opposite from going. But the second law tells us that it always goes this way. So it's called the arrow of time. I'll stop here. So check out the free energies video in a second, but I'm going to give you one last pause and tell you one last thing about entropy before we do that. See ya.